Welcome back to the 11th video about my full fly-by-wire electric outboard project. Last time we built a water intrusion detection that can discriminate between rainwater, freshwater and salt water. Card here, link in the description. Today I want to build a power supply that turns the 20 to 27 volts from our lithium iron phosphate battery into something usable for our electronics. We cannot always rely on our electronics being powered from a notebook via a USB cable, can we now? Enjoy! So, what are the requirements for our power supply? First, I want an input voltage range between 29.2 volts and 20 volts. Yes, I know, it's the wrong way around. 29.2 volts being the end of charge voltage for lithium iron phosphate batteries and 20.0 volts being their end of discharge voltage. Second, the output voltage should be between 21 volts and 7 volts. Again, the wrong way around. 21 volts being the maximum that the V-in pin of an Arduino Nano Every, respectively R4, can take. 7 volts being the minimum voltage an Arduino Nano Every needs at its V-in pin. By the way, that's only 6 volts for the new R4. And at that point, a big thank you to the viewer who commented on one of these videos about that new R4. I'm seriously considering switching over from the Every to the R4 now. Anyway, the lower the voltage, the more efficient the switch mode voltage regulators on the Nanos will work. Third, I want an output power of several watts. Yeah, I know, that's a little bit fuzzy. But remember, we will have RS485 communication, and an RS485 transceiver can draw in a short circuit situation 200-250 milliamps, so we need some power. Finally, fourth, I want electromagnetic compatibility, EMC. That means on the input side, we need an electromagnetic susceptibility, EMS protection, and on the output side, electromagnetic interference in accordance to Class B. Please note, Class B has lower emission limits than Class A. Yeah, it's the wrong way around somehow. Why do I want EMS protection? Well, in the end, we will have two 1 kilowatt Chinese brushless motors running here. And we will switch on and off two large lithium iron phosphate batteries. So yeah, we better have some protection in that area. And why I am so concerned about electromagnetic interference? Well, maybe I want to run a GPS or an AIS or a radio, and I want to run that, if possible, without any interference. We will build our power supply around a monolithic, non-isolated switch mode DC-DC converter. Non-isolated because our battery minus is connected to our circuit ground anyway, so an isolated switch mode DC-DC converter wouldn't make any sense here. And of course switch mode because our circuit is going into a watertight, airtight enclosure somehow. So we need the high efficiency of a switch mode converter. And yeah, forget about that 96%. That's just the marketing value. We could roll our own around a PWM controller or something, but yeah, remember, we want electromagnetic compatibility. And yeah, that would be a project in its own. So it was a monolithic DC to DC converter. I choose the Mornsun K78XX series, which are pin compatible with the linear LM78XX regulators. These kinds of DC to DC converters are available from half a dozen or more vendors. But I went with the Mornsun because they are cheap and they fulfill my requirements. One of them, which I haven't mentioned yet, is output short circuit protection, because I'm a noob. For our application, the 9, 12 or 15 volt model would be suitable. Both have a nominal input voltage of 24 volts, but they can eat up to 36 volts. Perfect. And the 15 volt model can go down on the input to 20 volts, the 12 volts to 16 volts, and the 9 volt to 13 volts. They all supply 1000 milliamps at the output, so we have here 9 watts, 12 watts, 15 watts, so our several watts requirement is also fulfilled. When it comes to efficiency, the 15 volt model is a bit more efficient than the 12 volt model, and the 12 volt model is a bit more efficient than the 9 volt model. Basically, the closer our output voltage is to the input voltage, the more efficient these things get. But remember, the same is true for the switch mode regulator on our Arduino Nano. And I rather burn my losses here in a rather large package than on the very small package which is on the Arduino. So I choose the 9 volt model, the K8709. When it comes to the specifications, there's really nothing to write home about. They're good enough. For example, voltage accuracy here is plus minus 3% maximum, and ripple and noise is at a maximum 75 millivolts peak to peak. Remember, we're just using that thing to feed another switch mode converter on our Arduino Nano. The important thing here is that they also specify the electromagnetic compatibility, EMC. For example, we have Class B emissions, and we have a whole lot here about the immunity. In addition, they provide a reference design for EMC compliant circuit. So our fourth criteria about EMC compliance is perfectly fulfilled. Here's the whole circuit with the values for all parts, which you can look up in the datasheet. Our battery voltage between 20 and 29 volts comes in here, and we tap that off after our current sensor. So this is labeled Motor Plus. And on the other side, we get 9 volt out for the V-in pin of the Arduino Nano. So first we have a fuse, and I haven't decided on the value yet. Then, for any really high energy spikes coming in here, we have a MOV going to the ground. And that MOV is of the type S20K30. Yeah, here are some vendor numbers for that MOV. And it basically starts to get conductive at 38 volts DC. And it can, at least for a very short time, absorb a current pulse of 2000 amps. Now you will ask yourself, okay, this is going up to 38 volts here, but our input is only good for 36 volts. So how does that work? Here comes that rather large LC low-pass filter element into play. So we have here a 82 microhenry conductor and a 680 microfarad capacitor. and anything the MOV is letting through should be absorbed here before it can reach the input of our DC to DC converter, at least according to the reference circuit of the vendor. So that whole part of the circuit is covering the electromagnetic susceptibility protection part. At the next capacitor and inductor, we have to turn things around, because this is also an LC low pass, and it's intended to filter out any electromagnetic interference coming out here of the input of our DC-DC converter to acceptable levels before it reaches the power rail. The inductor has a 12 microhenry and the capacitor 4.7 microfarads. Finally, we have a simple decoupling capacitor before the input of our DC to DC converter. Yeah, the current going in here is quite pulsed, 10 microfarads, and at the output we have a smoothing capacitor, 22 microfarads. And that's it. Let's have a look at the breadboards, and yes, I had to add another one here for the power supply. First, an overview. We tap off the battery voltage for our power supply after the current sensor. Here are also the connections for the motor, so that's why it was called Mod Plus in the circuit diagram. I moved the ground connection to the new breadboard, but it's also jumpered back here to the old breadboard, so we still have a common ground. Finally, the 9-volt output from our power supply will be jumped over to the VIN pin of our Arduino Nano. It's currently not connected. Instead, I have here 2 probes from my multimeter, so we can at first measure if really 9 volts are coming out here. Now for the details. Ground is coming here, so that's our ground rail, and it's immediately jumped back over to the first breadboard. Here is our battery, respectively motor voltage, coming in and going through a fuse. Currently 350 milliamps slow, but that's subject to change. Normally, after the fuse, we would have that big MOV going here to ground. Remember, that MOV, if there is a huge spike in the power supply, will conduct a lot of current to ground. That's the reason I moved the ground connection to this point. That jumper here is a stand-in for the 82 microhenry inductor, which I don't have. I also don't have that huge 680 microfarad capacitor that would go after that to ground. What I did have was that smaller 4.7 microfarad capacitor and that 12 microhenry inductor. Then we have that 10 microfarad decoupling capacitor at the input of our regulator and that 22 microfarad capacitor at the output of our regulator. And here are the 9 volts going to the VIN pin of our Arduino Nano. And now let's fire the whole thing up. As I mentioned before, the VIN pin is currently not connected. So power supply on, output on, and we got, wow, 9.29 volts. That's perfect. Let's connect the VIN pin now. Okay, the VIN pin is connected now, and I'm measuring here now the hopefully 5 volt rail from the Arduino Nano. So let's see. And 4.95 volts. Perfect. And you might not be able to see it, but the power LED of the Arduino also came on. And yeah, I'm not cheating here. We can remove the USB connection. Okay. That's it for today. Yeah, that was quite a vanilla job, yeah, building that power supply, but it had to be done. Anyway, I'm, as you noticed, running out of parts, so I have to put in another order for more parts. The problem here is I'm not quite sure which parts to order because, among other things, I want to reverse engineer and, if possible, improve the stock battery indicator that came with the Haswing electric trolling motor. Yeah. Anyway, so we will take a short break from the project at that point, and in the next video we will reverse engineer that battery indicator. Till then, bye.